What if we aren't alone? For all of human history, this question has echoed through our myths, our philosophies, and our science. We look up at the night sky, a tapestry of countless stars, and we can't help but wonder, is there anyone else out there looking back? This isn't just a question of idle curiosity. It touches upon the very core of our identity and our place in the universe. Are we a unique, fleeting accident, or are we part of a grand cosmic community? The answer, whatever it may be, will fundamentally change our understanding of life itself. To begin to grasp the scale of this question, we must first look at the numbers. Our home, the Milky Way galaxy, is a sprawling city of stars. Current estimates suggest it contains up to 400 billion of them. For a long time, we could only speculate if these stars had planets of their own. But in recent decades, our view has been revolutionized. We now know that planets are not the exception, but the rule. Astronomers believe there are more planets than stars in our galaxy, potentially trillions of them. And our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. The sheer number of potential homes for life is staggering, almost beyond comprehension. The universe is not an empty void, it is filled with worlds. In 1961, astronomer Frank Drake attempted to formalize this line of thinking. He created what is now known as the Drake equation, a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way. It's not a precise calculation, but a tool to organize our ignorance. The equation multiplies a series of factors: the rate of star formation, the fraction of those stars with planets, the number of planets that could support life, the fraction on which life actually appears, the fraction that develops intelligence, the fraction that creates detectable technology, and finally, the length of time such civilizations release detectable signals into space. While we have better data for the early terms now, the later variables, especially the lifetime of a civilization, remain profound unknowns. Depending on how optimistic or pessimistic you are, the answer could be millions, or it could be just one: us. This uncertainty leads directly to one of the most famous and unsettling questions in science: the Fermi paradox. In 1950, physicist Enrico Fermi, contemplating the high probability of alien life, supposedly asked a simple question: where is everybody? If the galaxy is teeming with potential life, and if even a fraction of that life develops intelligence and interstellar travel over millions of years, the galaxy should have been colonized many times over. We should see evidence of them everywhere. Yet when we listen, we hear only a great cosmic silence. This paradox has spawned dozens of hypotheses. Perhaps we are truly the first. Perhaps intelligent life inevitably destroys itself before it can reach the stars. Or maybe they are out there, but they are deliberately hiding from us, observing us from afar in a kind of cosmic zoo. Or perhaps the distances are simply too vast, and the universe is a collection of lonely islands, each unaware of the others. While philosophers debate the paradox, astronomers are busy gathering data. Our primary tools are the planet hunters. Missions like NASA's Kepler and TESS telescopes have discovered thousands of exoplanets using the transit method, watching for the tiny periodic dip in a star's light as a planet passes in front of it. Other methods, like radial velocity, detect the gravitational wobble a planet induces on its star. And now, with the power of the James Webb Space Telescope, we are entering a new era. For the first time, we can attempt direct imaging of larger exoplanets and, more importantly, analyze the chemical composition of their atmospheres. We are no longer just counting worlds, we are beginning to characterize them. The search for life hinges on finding biosignatures, chemical fingerprints in a planet's atmosphere that hint at biological processes. The gold standard is the presence of gases that shouldn't exist together without a constant biological source, like oxygen and methane. On Earth, photosynthesis pumps out oxygen, while microbes produce methane. Finding this kind of chemical disequilibrium on a distant world would be a monumental discovery, but we must be cautious. Geochemical processes can sometimes mimic life, creating false positives. The key is finding a world within its star's habitable zone, the orbital region where temperatures are just right for liquid water to exist on the surface. Water is the one ingredient we believe is essential for life as we know it. But what is life as we know it? Our own planet shows us that life is incredibly tenacious. We find it in the most extreme environments imaginable. We have extremophiles, organisms that thrive in boiling volcanic vents, in highly acidic waters, deep within Antarctic ice, and in the crushing pressure of the deep sea. These hardy life forms prove that the definition of a habitable environment might be far broader than we once thought. This realization has turned our attention back to our own solar system. If life can survive in such harsh conditions on Earth, could it not also find a foothold in the subsurface oceans of Jupiter's moon Europa, or the plumes of water erupting from Saturn's moon Enceladus? These ocean worlds are now primary targets in our search. Europa's vast hidden ocean may contain more water than all of Earth's oceans combined, kept liquid by the tidal forces of Jupiter. Enceladus conveniently sprays its ocean into space, offering us a chance to sample it without ever landing. And then there is Mars. Evidence strongly suggests the red planet was once a much warmer, wetter world, with rivers, lakes, and perhaps even a shallow ocean. While its surface is now a cold, irradiated desert, could microbial life have survived underground? Missions like the Perseverance rover are currently caching rock samples that a future mission aims to return to Earth. For the first time in history, we may soon be able to study pristine samples from another world in our own labs. Beyond searching for simple life, there is the search for intelligence. This is the domain of SETI, the search for extraterrestrial intelligence. For decades, SETI projects have used radio telescopes to listen for technosignatures, evidence of technology. The idea is that any advanced civilization might use radio for communication, just as we do. A deliberate beacon or leaked transmissions would stand out against the cosmic background noise as an artificial, narrow-band signal. More recent searches are also looking for other signs, like powerful laser pulses used for communication or propulsion, or even the atmospheric pollution of an industrial civilization. So far, the search has been met with silence, but our tools are becoming exponentially more powerful. We've only searched a tiny fraction of the cosmic haystack. In recent years, the conversation has also included unidentified anomalous phenomena, or UAPs. While these reports have captured public imagination, it's crucial to approach them with scientific skepticism. The scientific principle is that extraordinary claims require extraordinary evidence. To date, no UAP report has provided the kind of verifiable, unambiguous evidence that would be required to suggest an extraterrestrial origin. Many sightings can be explained by instrument errors, atmospheric phenomena, or human-made objects. Science demands rigorous, repeatable data, and until that standard is met, these phenomena remain just that, unidentified. This brings us back to the Fermi paradox and the sobering concept of the Great Filter. This idea suggests that there is some barrier or a series of barriers that is incredibly difficult for life to overcome. It could be the leap from non-life to life, the jump to complex cells, the evolution of intelligence, or the challenge of surviving our own technology. The question for humanity is the Great Filter in our past, or is it still ahead of us? If we are the only intelligent life we can find, it might mean we have overcome the hardest steps. But it also places a profound responsibility on our shoulders. If it is ahead of us, it serves as a stark warning about the existential risks we face, from climate change to nuclear war. So, what would an actual discovery look like? It probably wouldn't be a spaceship landing on the White House lawn. It would likely begin quietly, as a strange signal in a data set or an anomalous chemical reading from a distant world. It would be checked, rechecked, and scrutinized. Other teams around the world would try to replicate the finding with their own instruments. The process would be slow, methodical, and filled with debate. Confidence would build gradually, over months or even years, until the evidence became undeniable. The announcement would be one of the most significant moments in human history, a moment that would unite us in shared wonder. The search for life beyond Earth is a mirror. It reflects our greatest hopes and our deepest fears. It drives our technology, expands our knowledge, and forces us to confront the biggest questions of our existence. We may find that we are alone, the sole custodians of consciousness in this vast galaxy. Or, we may find that the universe is a garden, rich with a diversity of life we can barely imagine. Either answer is, in its own way, awe-inspiring. The quest continues. The sky is not the limit, it is just the beginning. If you find these cosmic questions as fascinating as we do, subscribe to Timelines and like the video to help us explore more of the universe's greatest mysteries.